This is Dutchess Community College, MAT 221, Calculus 1. This is a short video about the differentiation rules, the basics for the shortcuts to the derivative. If the derivative of a function is its slope, then for a constant function, the derivative must be equal to 0. So here's our first rule. The derivative of a constant function is equal to 0. Here's an example. A constant function, which is a horizontal line, like y equals 3, because the slope of a horizontal line is always 0, it makes sense that the derivative would equal 0. Likewise, for a linear function, the derivative must be the value of its slope. So if we have any linear function, or in other words, a function with a degree of 1, where we have x to the first power, the derivative of that function is going to be the slope of that line, which is, in this case, m. So an example would be, if I gave you y equals 2/3 x plus 3, the slope of this line is 2/3, therefore, this is equal to 0. 2/3. Now, what if we started with a function like y equals x squared? We saw that the derivative was equal to 2x, and this is part of a pattern. The pattern for this particular function, for any power function, x to the n, where n is a real number, the derivative of that function will be the value of the exponent dropped to the front, and then we subtract 1 from the exponent. In this case, the 2 gets dropped to the front, and we subtract 1 from 2 to get x to the first. Therefore, the derivative is 2x to the first. Here's an example. Using this rule, we have a power function, x to the fourth, where 4 is a rational power. Using this rule, the 4 would get dropped to the front, and I would subtract 1 from the exponent, so the derivative is equal to 4x to the third. Earlier in this semester, we found the derivative of this using the limit definition of the derivative, which was quite a lengthy process using the limit definition. We can see now that the shortcut will help our algebra skills tremendously. Here's another example. Y equals x to the 8th. Our derivative, dropping the exponent to the front and subtracting 1 from the exponent, gives us 8x to the 7th. This is called the power rule. Now, if I gave you a function f of x, and we know from pre-calculus that if I did a function 3f of x, that is a vertical stretch of the function f of x, and it would stretch the function by a factor of 3. If I gave you a function like 1/2 f of x, that would shrink the function by a factor of 1/2. That's a vertical shrinker. Remember, this is outside the function. If I put a negative in front and also multiplied by 2, we notice that from pre-calculus, we know that this would stretch the function by 2, but the negative value in front, remember, is a factor of flipping it or reflecting the function over the x-axis. Now, what about the derivative in each of these cases? What happens when I put a constant in front of a function? What happens to the derivative? Now, let's look at the derivative. I tried to draw the tangent line to the curve at x equals 0. So at x equals 0, you can see here's the tangent line to the curve. And you can kind of see that the slope is up 1/1. The slope is equal to 1 there. Now, what happens when I stretch that same function, f of x? What happens to the slope of the tangent line? Notice the tangent line now is up 3/1. Now it stretches the tangent line so that the tangent line has a slope 3 times the original slope. What about when I vertically shrink the function? you can see here the slope of the tangent line at x equals 0. The tangent line is here. Now we go up 1 over 2. You can see that the slope of that tangent line at x equals 0 is equal to 1/2. What happens when I do something like this? Notice I go down 2 over 1. So multiplying a function by a constant will stretch or shrink it, and the derivative is changed in exactly the same way. That brings us to the fourth rule, which is called the constant multiple rule. Here is the constant multiple rule in function notation. The derivative of a constant that's multiplied by a function, we can simply take that constant and pull it out to the front and then take the derivative of the remaining part of the function. Now I'm going to give you some easy ones here to start with. If I combine this with the power rule, what happens is that constant times the power function, the constant gets pulled to the front, and then I use the power rule that I just did, that coefficient comes to the front, and then I subtract 1 from the coefficient. So using it on the power rule, this is using both the power rule and the constant multiple rule. That 7 is a constant in front of the power function. The 7 would get pulled out. Then I would take the derivative of x to the 5th, which we just found out was 5x to the 4th, which gives us 35x to the 4th. Now you might say at first, like, why is this even a rule? Couldn't we just multiply them through? You'll see with power functions it's very simple, but with other functions this is going to be a really important rule to have, to be able to pull a constant out of a function and then take the derivative of the remaining part of the function. Rules 5 and 6 are the sum and difference rules. And again, they're pretty much no-brainers, pretty basic rules. The derivative, if you have a function plus another function, is simply the derivative of the first function plus the derivative of the second function. Likewise, if I have the derivative of a function subtracted by another function, it's simply the derivative of the first function minus the derivative of the second function. So the sum and difference rules are pretty simple. We would just keep the addition or the subtraction and take the derivative of each piece as I move across the function. So an example of this, using the rules we have so far, this first part of this polynomial function is a power function. And using the power rule, this first derivative would be 4x to the 3rd, dropping the exponent to the front and subtracting 1 from the exponent. The plus simply gets brought down. And then I look at the second part, and this part right here is a linear function. Remember, if I had y equals 12x, that's just a linear function with a slope of 12. And we said rule number 2 was that the derivative of a linear function is simply its slope. So in other words, when I have x to the first power, I simply take the coefficient that I have there. So the derivative of this function is 4x to the 3rd plus 12, using the power rule, the linear rule, and again now the sum rule. We simply take the derivative of each term treated separately. Here's another one. Let's try this one with the rules that we have so far. The first term would become 4x to the 3rd. That's using the power rule. The subtraction would just get brought down. That's the subtraction rule. I would take the derivative of this next function. This is using the constant rule. That constant in front of the function would just get brought down and be a 2. And then I would take the derivative of x squared using the power rule, which would be 2x to the 1st. And 2 times 2 would give me 4x to the 1st. I would bring down the plus sign. And then I would have a constant function. 2 is just a constant number, no variable. And that was the first rule we did, which was 0. So the derivative of this term would be 4x to the 3rd minus 4x. What about if I asked you to find the horizontal tangent lines of this particular function? Notice this is the function I just found the derivative of. We found the derivative was 4x to the 3rd minus 4x. If I want you to find the horizontal tangent lines, that means I want you to find where the derivative is equal to 0. Where the tangent line would be horizontal. So we're going to set this derivative equal to 0 to find out what values of x does this occur at. Doing a little bit of factoring here, a little bit of algebra, I divided everything by 4. I factored out an x. I factored that term to get my 3 terms, and I set each term equal to 0. My 3 factors here is when x equals 0, x equals -1, and x equals +1 would give me horizontal tangent lines. But remember, the actual equation of a horizontal tangent line is the y value that occurs at each one of those points. So I would take those values of x and plug them into the original function back up here. When x equals 0, y equals 2. When x equals -1, y equals 1. And when x equals +1, y also equals 1. So my 3 tangent lines are y equals 2, y equals 1, and y equals 1. Now you might say to yourself, why do I need 2 here? This is actually the same tangent line. It just comes about because of the symmetry of this quartic. If we got back to precalculus and looked at this quartic and graphed it, this is an even function that has symmetry around the y-axis. And so you can easily see at x equals -1 and at x equals +1, that tangent line is going to be the same line, y equals 1. So our tangent lines, if drawn, are y equals 2 at x equals 0, and y equals 1 at x equals -1 and x equals 1. If I then actually graph the function that is the derivative function, that was the derivative 4x to the third minus 4x, which is a cubic function, would look something like this. And you can see that the derivative function would have 0 values when the original function has horizontal tangent lines at x equals 1, at x equals 0, and at x equals 1 and -1. Last thing I want to talk to you about in these basic derivatives is sometimes it's easier that before we actually compute a derivative, we can rewrite a derivative. Now we're going to eventually get to a rule called the quotient rule, but something like this where we have a monomial denominator, sometimes it's easier to take the derivative by rewriting the function first before we take the derivative. In other words, in this case, let's take the derivative by first taking the denominator of this function and dividing each term of the numerator by the common denominator of x. When I do, I have to then remember our rules for exponents, that when I divide a variable of the same power, of the same base, remember I subtract the exponents. This is a precalculus topic. Here I get this as my function. Notice I have not taken a derivative here. I've simply simplified the function first using my monomial denominator and using my rules for exponents from precalculus. Now we can go term by term across this expression to find the derivative. This first one is a linear function. Remember, the linear function is simply the slope. That would be 4. This is a subtraction rule, but this is just a constant, and we know the derivative of a constant is 0. This is the plus rule, or the sum rule. We would just bring down the plus sign. This is the constant rule. I would pull that 3 out to the front. Then I have the power rule, so I would multiply this by -1/2, and then subtract 1 from the exponent to get -3/2. Here's my derivative, which is simplified as 4 minus 3/2 x to the -3/2.